This question asks us to use the differentiability of the power series to find the sum from n equals 1 to infinity of x to the 3n over n as an elementary function. So we're going to find this series as defined as an elementary function and establish the radius and interval of convergence for the series. So the differentiability of power series means that we can take our series here and differentiate it. So we're going to differentiate our series, just put it in brackets here. X to the 3nth power over n. Well, by definition, we know that we can put our d dx to the inside of the series here and treat it just like if it were a function or something. So here we have the sum from n equals 1 to infinity, and we're just going to put our differentiation here on the inside of the series. And this n down here in the denominator, we're just going to treat that like a constant. So we can actually pull that outside of our derivative here. So I'm just going to pull the 1 over n outside of our derivative. And we have d dx of x to the 3nth power. Well, we know how to do this. This is just going to give us our sum from n equals 1 to infinity of 3n over n. So this power of 3n here, I'm just going to pull it out front, and then we'll subtract 1 from all of this. And the n and the n here are going to cancel. So that would just give us 3n. We just put what was in the power here out front by definition of our power rule of differentiation here. The n and the n are going to cancel, and then we're going to be left with a x to the 3n minus 1. So the n's cancel, and then just gives us the sum of 3 times x to the 3n minus 1. Well, the first thing that I would do is I would see if there's some way that we can change this n equals 1 here to a 0. Because if we could get this to a 0, then maybe we might be able to manipulate this to where it looks more like a geometric series that we know how to work with. So that's what we're going to do. Let's see, just bring this over here. So we're just going to start working over here. This is going to be equal to if I make this n a 0, well then I know that I have to increase n by 1 here. because we're subtracting 1 here, so we have to add 1 up here. So this is going to give me 3 times x. Now here we want to be careful. You can't just add an extra 1 to this. You have to add 1 to n specifically. So whatever is out in front of it n that it's being multiplied by will also multiply times what you're raising n to. So this is 3 times n plus 1, and then we still have our minus 1 over here. And this is going to equal the sum from n equals 0 to infinity of 3. Here we have 3 times n, which is going to give us 3n. 3 times 1 is 3, minus 1 is just positive 2. So that's going to be 3 times x to the 3n plus 2. Well, again, we can manipulate this algebraically, and that will get us, squeeze this over here on the edge, n equals 0 to infinity of 3 times 3 times x squared times x cubed to the nth power. And if you want to just pause the video and just double check my algebra on this, don't just take my word for it, because you'll learn more if you actually work through and think through the steps yourself. So now we have manipulated this. We've taken a derivative. Remember that we took our derivative here, so we'll have to integrate at some point. And we have algebraically manipulated this to where it looks like a geometric series now. So this 3 times x squared, that's just going to be our a value. And this x cubed to the n, that's just going to be our common ratio. So we know that along the interval of convergence, this is just going to equal our a value, which is 3x squared over 1 minus our common ratio, which is x cubed. But because we took our derivative here, because we differentiated, we're going to have to integrate this to figure out what that elementary function was. So we are going to integrate. This is the next step here. We're going to integrate, just take the indefinite integral here, of 3x squared over 1 minus x cubed dx. And the first thing that might jump out at you is that we can do u substitution here. Let's let our u equal 1 minus x cubed. Then du is just going to equal negative 3 x squared. Well, we can manipulate this a little bit. We don't have a negative 3x squared here, but we can make this be a negative 3x squared. And because we put a negative here, we're going to have to multiply the whole thing by negative 1. We could take our negative out there. So the negative would ultimately cancel out. But we've got it to a point now where we can do u substitution. So this is going to equal the negative integral of just 1 over u du, and we know how to integrate this. Don't forget your negative. And that's going to equal the negative natural log, or the log of e, to get to u, the absolute value of u, plus some sort of constant, we don't know what it is, c. And remember that u just equaled 1 minus x cubed. So we'll substitute u back for 1, the absolute value of 1 minus x cubed. All of that plus some constant c here. So when we take the integral, when we take the series that we've started with here, the sum from 1 to infinity of x to the 3nth power over n, we know that that is going to be equal to this. So let me just section this off here. We know that that is going to equal the series that we started with. That's the series from n equals 1 to infinity of x to the 3nth power over n. Now, we just have to solve for c. And if you let x equal 0, that looks like the easiest way to do that in this case. Other times you might want to solve for when x equals 1 or whatever, so you can get terms to cancel out or become simpler and make the expression more obvious. When x is equal to 0, well, this is just a 0, and then your natural log of 1 is just 0, and of course negative 0 is just 0. So when x is at 0, I like using the at symbol, we just have, this is all just 0. So that c is equal to, let's figure this out. When x is equal to 0, then we would have 0 to the 3nth power. Well, an infinite sum of zeros is just going to equal 0. So we have that our c equals 0. And then we're in the home stretch here, because we have shown that our series from n equals 1 to infinity of x to the 3nth power over n is just going to equal the negative natural log of the absolute value of 1 minus x cubed plus c. Oh, I'm sorry. We established that c equals 0. I was just blindly copying. You have to be careful about that. So it equals the negative natural log of the absolute value of 1 minus x cubed. Now the only thing that we haven't done here is we haven't established the radius or interval of convergence. And just for the heck of it, let's go ahead and do that. So if we do our ratio test here on our series, or our b sub n part of our series rather, that gives us that the limit n approaches infinity of the absolute value of x to the 3 times n plus 1. Now be careful, it's not as simple as just adding a plus 1 up here, because we're multiplying 3 times our n plus 1 over n plus 1. All of that over our b sub n here, which is x to the 3nth power over n. Well, that is just going to go to, let's see, here we have x to the 3n. That's going to cancel out with this x to the 3n here. That's just going to leave us with a x to the 3rd power. And then the limit as n approaches infinity of n over n plus 1. Well, that's just going to go to 1. And what we're going to be left with is a x cubed. So we know that this x cubed, we know that x cubed has got to be greater than -1 and smaller than 1. Well, you know that 1 cubed is just 1, and -1 cubed is just -1. So we could just say that -1 is smaller than x, and x is smaller than 1. So we've established our radius of convergence here. We know that our radius of convergence is just going to equal 1. If you just imagine that x is at 0, well then -1 and 1 are equidistant from 0, and that's just a radius of 1. So our radius is equal to 1. And our interval of convergence, well, let's think about what happens when x is equal to -1. When x is equal to -1, well then we just have -1 cubed, which is -1, to the nth power, and then we just have our alternating harmonic series, which we know is convergent. And when x is equal to 1, then we just have 1 cubed, which is just 1 to the nth power, which is just going to be 1, and then we just have our divergent harmonic series. So we know that this is not part of our interval of convergence. So we could say that our interval of convergence here is going to include -1 and exclude 1. And we are done.